Did you get it? Okay, I'll start. Dear Father, we thank you for this day. Again, Lord, I thank you for these students. Pray you to bless this class. Help us to, again, Lord, glorify you, what we do, Lord. In your name I pray. Amen. All right. Let me foolishly attempt to derive something. So I want to talk about second derivatives and parametrics. And so there are some formulas in the book which I will foolishly not look at. And so our goal in this little discussion here is to understand dy dx and d squared y dx squared when y and x are given parametrically. All right. So let me be a little bit picky here and say that x is equal to, let's say, f1 of t, and y is equal to f2 of t. All right. So these are parameterization of some curve. So in this context, how would we understand let's see here. Well, let's see. If this was also equal to, suppose this was also equal to g of x. So I'm going to switch things up here a little bit. Let me say that's g1, and that's g2. I'm going to make this f. That may be more natural. Suppose we're talking about, I'm going to talk about a curve. All right, so the curve I'm going to think of, we can either look at it as y equals f of x, okay, or the other way we have to describe it is parametrically. X equals to g1 of t, y equals to g2 of t. Does that make sense? I mean, we have these two competing descriptions for the curve, either as a graph or parametrically, okay? I want to compare and contrast these two worlds. So what does it mean if this is given, all right? Suppose this is given. All right. What does it take to find a parameter? What does the parameterization have to do to actually solve this be consistent with this graph? I mean, we have to have that, g2 of t should be equal to f of g1 of t, right? Now, but this is nice because we can differentiate this and understand the relation. So if I differentiate this, I get g2 prime, right, equals to what? Equals to f prime of g1 of t times g1 prime of t. Right? And so what does this tell me? Therefore, f prime of g1 of t equals to g2 prime of t, right, divided by g1 prime of t. Provided what? Yeah. Now, what's our usual language? I have not been using g1 and g2 in our applications, in our discussion in here, right? Because it's just, to me, far more natural to usually write here, that's f prime of, x of t is equal to what? It's equal to y prime of t divided by x prime of t, right? Or better yet, this is dy dx at x of t is equal to, well, dy dt divided by dx dt. But you see, this is just, this formula right here is nothing more than a convenient reformulation in terms of notation we've accepted. Right? I mean, the calculus I've done carefully with those, but really, this is a nice, slick formula that expresses the same truth. So with this in mind, it's pretty easy to see how to derive the second derivative, right? So if I just go back, if I go here, and I differentiate that again, that will reveal to me how f prime prime is related to the parameterization of the graph, right? Differentiate this again, what do we get? We get g2 prime prime of t equals to, well, the derivative of this product, right? So how's that go? Product rule, right? So that's f prime prime of g1 of t times g1 prime of t times g1 prime of t, right? Plus f prime of g1 of t times g1 prime prime of t. Now this thing right here is what we would like to call d squared y dx squared at g1 of t, right? This again is dy dx at g1 of t, right? So we can solve this for d squared y dx squared. What do we got? Divided by what? Oh, I'm sorry. I did a bad thing. This is what? Right. And I'm supposed to divide by, I was solving for this, so I've still got this coefficient. So I have to divide by g1 prime of t quantity squared. It's funny. It kind of looks like almost looks like a quotient rule. It's not that, but it kind of looks like it. Now, you could, of course, you could leave it like this, or you could use what we already know, which is that this piece right here, right, can be traded for what? It can be traded for this right here, right? So this is actually equal to g2 prime prime t minus g2 prime t over g1 prime of t times g1 prime prime of t divided by g1 prime of t squared. But why have two fractions when you can just have one? Multiply the top and the bottom by the derivative of g1, and what's it give us? Gives us this nice symmetrical kind of formula in some sense. Not really. There's a difference between x and y because we're thinking of y being a function of x, and they're you know, the asymmetry is not coming from the parameterization. It's coming from the fact that we're thinking this curve is the graph of a function of x. And so there you go. The usual notation for this, of course, is x prime y prime prime, bad notation. So let me say that this is x dot y, oh, stink. What have I done? Yeah. Fine. This is where it gets annoying. So this is the danger. X prime of t, y prime prime of t. Excuse me, guys. Oh, goodness gracious. X prime of t. Gah. Whoa. No, that's y prime. I can't count. 2 is y. Y prime, yes, it must be the sneeze. Yes, that's what it is this here. X prime prime of t divided by x prime of t cubed. So, what happened?
Oh, I got something out.
Oh.
But it's good.
It's good?
Yeah.
Okay. You're worrying me.
Sorry.
It's fine. So we can use this to study, for example, concavity of a function that's parameterized, right? Like here, application. If we have x equals to, let's say, t cubed, and y equals to t squared, right? We can ask the question, is this concave up or concave down at t equals to 1? You know? So the question is d squared y dx squared, you know, at, well, at 1, right? T equals 1 is x equals to 1, isn't it? Right? So if we use the thing I just derived, we should do, what's x prime? X prime is 3t squared. What's y prime prime? It's 2. And then we're supposed to subtract y prime, which is 2t, and x prime prime, which is 6t. Thank you. And that's supposed to all be divided by x prime, which is 3t squared cubed, right? Now, this is supposed to be evaluated at t equals to 1 for my given question, right? And so what's that give us? That gives us really... Oh, I'm sorry, I can't do math. Oh, yeah, I thought it was 0 for a second there. 6 minus 12, right, which is minus 6 over 27? Okay. Right, that's less than 0, so that implies that the curve is concave down at 1, 1. I know it's 1, 1 because if I put t equals to 1 into the y formula, I get 1, 2. Was it?
So that's just a standard form we can use to determine the concavity.
Yeah, if you want to judge the concavity of a parameterized curve, that's a formula you need to know. Otherwise, I don't know. Yeah. It's kind of tough, yeah. So does that help, Josh? You asked me about that. That's why there's a cube down there. It's ultimately because of an algebraic simplification that, but I don't.
I guess that helps explain what they do here. Would another, is that also never mind.
I mean, because you were thinking some sort of just formal analogy that the second derivative should just have like a square down here, right?
Yeah, I was.
But that's just it's kind of a quirk of the calculus here that this happens. This is a fortunate accident in some sense of the formulas. The second derivative, it's not just the second derivative is not the square of the first derivative. It's the change in the first derivative. So it's more kind of more complicated than just that.
So, with over here, when they take the second derivative, it seems as though they just leave dx. It seems as though they take the first derivative. They leave dx dt alone on the denominator.
Yeah.
In the numerator, they take the derivative of the answer to dy over dx, and that's the new numerator.
Well, excuse me. I think I'm not sure if I should agree or disagree with you at the moment, Josh. Excuse me. They are putting forward the sort of excuse me. We can look at this also as ddx, right? Acting on a function is in some sense, in this interpretation, it is 1 over dx dt, all right, times d dt. Like that's how to change an x derivative into a t derivative. So if I do 2 of these, if I do d squared dx squared, that's understood to be ddx right? But the thing is, that is 1 over dx dt of 1 over dx dt times ddt. If you want to look at it as an operator equation. And that's why it's not just squaring, because you actually have to differentiate this. I mean, to really understand this, you have to look at it acting on a function, say f, right? So when this happens, we get, by the product rule, if you like, minus 1 over dx dt squared times d squared x dt squared times df dt plus 1 over dx dt d squared f dt squared.
Okay, so what they do over here when they take the second derivative, the same kind of trend would not happen if they were to take the third derivative.
If you were to take the third derivative, it would, I mean, he has the formula here. I mean, he has a path towards finding the third derivative. I just gave you a stone cold formula to calculate second derivatives, right? I mean, I don't like to do this, but here's a black box. You can use that to calculate the second derivative. Let's see here, how to say this. Let's see here. Let me do this calculation without the black box, the book way, okay? Book method. I think what he's saying is to calculate d squared y dx squared, what you should do is you should say, well, that's 1 over dx dt, right? Times d dt of dy dx, right? But what is that? And that's probably, I mean, this is probably a better way. I mean, I haven't thought a lot about these things, so I don't have a really firmly ground opinion as to what's optimal here. That's 3t squared, that's my dx dt. What's my dy dx? See, that you could figure out as a separate calculation. Dy dx is y dot over x dot, which is 2t over 3t squared, which is, 2 over 3t. So that's kind of nice. So the formula that you're talking about, Josh, those are a roadmap towards doing what I'm doing right now. Oh, I'm sorry, I'm just writing it down again. Let's actually do it. 3t squared, what we got here? Minus 2 over 3t squared, I believe. Which is what? Oh, I think I did. I think I just did, what is it again? I'm sorry.
-2 over 9 t to the fourth.
What is this? -6 on the top, right? Because 6 minus 12 is -6. T squared divided by 27 t to the 6th, which is what? Cancel the 3's.
-2 over 9 to the fourth.
Oh, wait, yeah. Yeah. So it's the same thing. I mean, the book's way is not wrong. It's just, you got to understand what he means by that. I mean, he means you find dy dx as a function of t, then you differentiate that. But after that, you still have to multiply by the reciprocal of the x speed to get the second. So you see what he means then by the third derivative. See, we could actually, now that we understand.
So yeah, what he does that wouldn't be done again with the third derivative.
So we do ddt of the dy dx, d squared y dx squared, right? Which we already just figured out was -2 over 9t to the 4th, so you could do that. So I hope you can see the merits both of the formula that's in the box versus this way of thinking. I mean, I feel like both actually in their own way. What's dx dt? So 1 over 3t squared times 8 over 9t to the 5th, yeah. So. Yeah. So if for some reason you wanted to find, like, you know, points of inflection and things like that, this would be the kind of thing you want to do.
Is that what is after concavity?
Yeah, yeah. I mean, that's, for me, the second derivative tells me about concavity. Or acceleration, if you like, yeah. Can I erase these things? I mean, I just wanted, I thought I should derive this for you guys because it's something that was left out of. We spent a long time thinking about how to find formulas for different curves, right? We didn't spend as much time on how to actually do this kind of calculus, so I think it's warranted. And if you're confused about where things come from, for me, you got to go back to the basics and like start and just do calculus 1 and just understand the notation. Excuse me. Any question? Oh, okay. So you guys ask about your homework then, and I will do my best to give hints and not to actually solve any of them. 10.5, number 22. All right, let me see. That would be good.
Finding the proper bounds really puzzled me on this one.
We're supposed to find the area of the polar region. He says to use a graphing utility, but we will use our method, which is to graph. All right, r equals to 2 times 1 plus 2 sine theta. And he says find the area between the loops. So any problem like this, the only way you can solve it is to first graph the polar equation, right? And I don't think you need a graphing utility to do this. In fact, I think that that's silly to say that you need a graphing utility. We can do this with our basic technique. So this is r equals to 2 plus 4 sine theta. We can graph that, right? This, excuse me. So we're working around 2, right? And we're going plus or minus 4 from there. So we're going to 6, and we're going down to minus 2, right? 4 above, 4 below, and it's sine theta. So my graph isn't quite right. Yeah, anyway, you'll do better. But anyway, so basically this is one of these dudes, right? And I could go past that, but that's probably enough to see what goes on. I've worked a few of these with you guys lately, so I'm pretty sure that that will suffice to make the graph, all right? So again, this is a plot of r versus theta. And I can use that to make the graph of the function that we're looking at here. So what is that? I don't need to have the most beautiful graph. I just need to have a graph which captures the essential features. And I think, I said that this would be enough, but I just want to go back here a little bit more to there. It makes me feel better to start there for some reason. That would be where, let's see here, let's put some of these points in. What's this? This is pi, right? This is 2 pi. The maximum is pi over 2. That's 3 pi over 2, right? At theta equals to 0, where is it? It's at radius 2, right? So maybe the graph starts there. But if we go back to here, which would be what, like, I'm not sure. This is a little bit negative. I'm not sure exactly what that point is, but let's see here. To get r equals 0, what would I can figure it out in a second. I think it's minus pi over 6, actually. So like minus 30 degrees, which is something like down here, right? This thing swings back to 0 from here to there. All right? So that's this piece right here. And then, let's see here. When we get to pi over 2, we're at radius 6, right? So it's like out here somewhere. Let me call that. Let's see here. Then I'll do some color coding for the next part. Then I swing back to 0 again, right? Interesting. This, I believe, is 7 pi over 6. You can figure it out with it. Anyway, it's clear enough. It actually doesn't really matter exactly where that is. The point is, a little bit past pi, it swings radius back to 0 again, right? But like that. All right, so that's this coming from this part of my graph here. Yep.
When for the particular chart, the XY chart.
Yep.
When you go from pi over 2 back down to pi, how do you know to put it in that shape curved like that? Like why not curved more outwards or more in?
Because the radius goes from 6 down to 0, a little bit past pi. It's radius 2 at pi itself. So really this should be more symmetric. That should also be 2. It should be the same distance from here to here. It's 6 out to here, and it goes from 6 down to 2 as it gets there. And then it goes from 2 to 0 as it goes from there to there. So it kind of forces that shape.
Like, how do you know how far it goes out, though, before it turns back to 2?
Well, if it did something like this, then there would have to be a corresponding lump over here. There would have to be a, like one of these deals or something. I mean, but there's not. It just decreases. So that doesn't happen. Again, you can follow points. If you don't see the pattern, you can pick a series of points and track them and then connect the dots. But I think this is faster personally. But now the next piece here, going from 7 pi over 6, right? Like this piece in here, that's going from where? Going from 7 pi over 6 to, where's this? This is, I think it's pi over 6 shy of 2 pi. It's 11, 11 pi over 6. But that, where is that? I guess it's actually this again, right? So that's between here and here, right? So in principle, it goes to radius 2 again. So you might think that it would look like, I'll do it dotted. It would look something like this, right? But that's not right because this is negative radius. So it flips up to make the so-called inner loop. At which point, we've come full cycle. And then we just repeat the story again. So now what's the question? It says find the area between the loops, right? So now we see what it is, right? It's this area up in here, right? Now, I think the way I would do that would be I would find the area of the sort of cardioid-looking. That's all. Not a very good picture. It's like a deformed tooth or something. But the outer thing, and then I would subtract the area of the inner thing. And that would give me the area. That's how I would think about this. Take the area of the big thing minus the area of the inside thing. I don't want to try to do it as one integral because the same function is defining the inside and outside radius. So r in squared minus r out squared is not a good option here because that would require some kind of more delicate thinking that we'd rather avoid. And so the question then is, what range of theta is the outside loop happening for? Well, it's happening for minus pi over 6, less than or equal to theta, less than or equal to 7 pi over 6. Assuming that we probably should actually take the time to be sure about that, huh? This equals to 0 gives me what? So sine theta equals to what? Minus 2 over 4, right? Minus 1/2. So that says that theta is minus pi over 6, yeah. Okay, good. I didn't just make that up incorrectly. Good. So this, if I integrate from here to here, that gives me the area of that. And the inside loop is what? It's 7 pi over 6, less than or equal to theta, less than or equal to 11 pi over 6, right? So the area integral, 1/2, the radius squared, which is what? Oh, well, it is what it is. It's I mean, it's not bad. It's just, I'm not going to actually do it. I'll just set it up. I think the setup is the thing that you're most curious about, right?
Yes.
So that's the big area, and then I subtract from that the little area. And why am I doing? I'm doing 1/2 r out squared minus r in squared. But in this case, I'm thinking of the inner radius being 0 as a way to do this. Yep. The if I have a region. Oh, that's not a very good one. Sorry. If I have a region like this, all right, that's still not very good. Stink. I'll eventually come up with a picture I'm happy with. If I have a region like this, if we do that, we need calculus 3. So, all right, here we go. And suppose this is theta 1, this is theta 2. Then we explained the other day that the area for this region is equal to the integral theta 1 to theta 2 of 1/2 r out squared minus r in squared d theta. Now that half has to, so in this case, I'm, you know, the inner radius is 0. If you go from the origin to any point, you're staying within, this is supposed to be straight, thing over here, again, you know, straight. The inside radius is 0. In here, if I go from the pole to the shape, then the inside radius is not the origin, it's that in my picture. Now the half has to be there. Here's an example. How about this? Circle, right? Radius equal to r, let's say. Calculate the area. Integral from 0 to 2 pi, right? 1/2. What's my r? Well, my r is just r squared d theta, right? Which gives me what? You know, so that half has to be there because of the way angle measure relates to area. Other questions? So I think it's a good question to ask. I don't think we've done quite enough of these. I mean, you should do enough of these that you're comfortable with them. It's definitely a question on your test, something like this. I'm not fond of this example particularly. This one's got a little bit something. This one's a little bit nastier than what I probably will ask on the test, but you know, it's definitely worth doing. Otherwise, I wouldn't assign it. Other questions? You guys are relaxed. This break was effective.
Well, nobody has anything else. Could we look at 10.1, number 17, part B? For some reason, this is in front of me. It
Uh-oh.
shouldn't.
Well, all right. Let's see here. 10.1, number 17, huh?
70.
Oh, 70. Uh-oh.
Yeah. We'll just part B.
Part B, though. Yeah, I think the back's
All right, so we've got a cable bridge. suspended in the shape of a parabola between two towers, 120 meters apart, 20 meters above the roadway. So here's a picture, like so. And so this point is whatever. We're just focused on the middle part here. And he says put the y-axis in the middle. Great, do that. Why not? Let's go nuts. This point is 60, comma 20, which means this point over here is minus 60, comma 20, because he tells us it's 120 meters, right? Cable touches the roadway midway, so the origin is also a point here on the parabola. Find the equation for the parabolic shape of the cable and find the length of the parabolic cable. All right. So it's pretty clear that y minus 20 should be equal to x minus 60 times x plus 60. Yes?
Sure.
What did I do? I said, I forget about, yeah. You can think about the problem as it's given, but isn't it a lot easier to think about a parabola which has its sort of x-intercepts here, right? So if it was like that, everyone would write down x minus 60 times x plus 60 because it's got intercepts, right? But that's not honest because y equals 0 is down here, but that's easy enough to fix. I just subtract 20, and this has to be the formula for it. And you can see that this formula fits those points because if I put in x equals to 60, I get y equal to 20. Put x equal to minus 60, I get y equal to 20. Now suppose you don't have, I have my methods. Suppose you don't, this is, I don't know what to call this. This is magical guessing, okay? There's a method to my madness, but maybe you wouldn't see it that way. How would you do this otherwise? How would you find the equation? Here's how I'd do it. So generically speaking, y is equal to ax squared plus bx plus c, right? I've got 3 points. I plug them in. Fit a, b, and c. Simple as that. So y of 0 is 0. It's also equal to c. 1 down. Y of 60 is equal to 60 squared a plus 60b. Y of minus 60 is equal to 60 squared a minus 60 squared, right? Fine, I'll write it. Minus 60 squared a minus 60b. Now this is equal to what? These are both equal to 20, right? So I already know c is equal to 0. Great, got that done. 2 equations, 2 unknowns. You can solve 2 equations, 2 unknowns. Not a big deal, right? Add them. Add them. What happens? You get 2 times 60 squared a equals to 40. Therefore, a is equal to what? 40 divided by what? Man. How is it that I... What'd you say? Really? All right. Yeah. Yeah, anyway, 180. And then if I subtract these, I get what? I get 120b. Oh, I see what I did. This is coming out. I was like, this is nonsense. This is bad. And see, I did something very bad. What did I do? Oh, no, man. I just learned C was 0. That wasn't wrong. Ah. Why did I erase? Oh, my goodness. Have you ever had that feeling? You just erase something and then really, really regret doing it. No. Well, I think B is 0. A is what? 1 over 180. That doesn't seem right. Doesn't seem right at all.
Can we just multiply that one out to check?
Oh, I'm sorry, but yeah. So this is telling me y is equal to 1 over 180. I mean, if I just trust the math, it's that. What happens when I simplify this? What do I get? X squared what? Minus 3,600. Well, that's I mean, there's something wrong with my thinking over here.
Oh, yeah.
I did this part A by using the standard form of the equation of the parabola with, the x minus h squared equals 4b. That's why this came out.
Yeah. Plus 20. Yeah, I know, but I don't. I'm not disagreeing. I don't believe in it. See that if I plug in x equals to 60 or minus 60, I do get y equals to 20 there. But but what happens if I plug in x equals to 0? What happens when see, this isn't quite right. This is not quite right. Yeah, see, that's the thing that's wrong with this. I have to put in a, and I don't know what a is a priori before the fact. That's what's wrong. Because that a is needed, because yes, I fit these 2 points, but I neglected the middle one. Right? And the thing is, there's tons and tons of parabolas that go through those 2 points, but don't hit the middle one. There's like this parabola, and there's this parabola, and there's this parabola, and there's that. You get the idea. There's tons and tons of parabolas that go through those 2 points, but don't hit the origin. I need to pick a specific a to hit the origin. To get that, I actually have to put minus 20 equal to a times minus 60 times 60, which will give me that a is equal to what? 20 over 3,600, also known as. All right, now I'm happier. All right, I feel better. So this formula is legit. As you can see, my method of guessing has to be supplemented with checking. You got to be suspicious. When you make up madcap guesses, you need to check on them. This, on the other hand, is a kind of stodgy standard technique that comes at the cost of doing algebra that we can do. And this formula is the real deal, because if we plug in 60 or minus 60, we get 3,600 over 180, which is 120, which is 20 in both cases. But then, so that's part A, which you could do anyway. Part B is what you're stuck on. So find the length of the parabola.
Yes.
So the length would be the integral from minus 60 to 60 of the square root of 1 plus dy dx squared dx, arc length. Which, of course, we could be lazier, say 2 times the integral from 0 to 60 of the square root. And that's not bad. That's, what is that? 1 plus, what's dy dx here? It's actually just x over 90. Yeah?
Why use that integral instead of, well, why wouldn't you use, why wouldn't you take the integral from 60 to minus 60 of y, the function for the arc, for the hyperbola?
It tells us that, I am. Y equals to 180x squared. I have to differentiate it, though, right? I mean, the formula for arc length is to integrate 1 plus dy dx squared square root over dx if we're going to calculate the arc length of a graph. This is the arc length of a graph. This is a graph, so I don't... What are you asking? I guess the question is, can you do this integral? How would you do this integral? Google. Google. Hurt me with that. How about, we remember cos squared theta minus u substitution doesn't work because you get an extra x which you don't have. So cos squared theta minus sinh squared theta is un. So cos squared theta is 1 plus sinh squared theta, which makes me suggest that we should put x over 90 equal to the hyperbolic sine of theta. So then, this is 2 times the integral. Now, 0 maps to 0, but if we put 60 over 90 equal to sinh theta, that suggests an upper theta bound of inverse sinh of 2/3. And this is the square root of cos squared theta. Dx is what? Well, dx is 90 cos theta d theta, right? And so we get 2 times the integral from 0 to inverse hyperbolic sine of 2/3 cos squared theta d theta. I would remind you that cos squared theta, I mean, there's various ways to do this. Here's one I'm fond of. This is 1 plus cos 2 theta. And there's a 90 I just lost. So the 2's cancel. We get 90 times the integral of 1 plus the hyperbolic cosine of 2 theta d theta, 0 to inverse sinh of 2/3. Sorry, it's getting small. But anyway, you can finish the integral, right? If you sort through it in exponent, I mean, you could actually find an exact value here. if you sort through the trigonometry. I have an example I'd like to show you guys, actually. I keep forgetting to show you this, guys, but get it out. So when's the math battle this week? Thursday. So you guys got one more day to ask me. So you guys are mostly done with your homework then, since no one has questions. Is that fair? No? How many people? We go 1, 2, 3, 4, 5, 6, 7, 8, 9. We're down to 10. There's still 14 people registered for this course, so I'll assume the other 4 people are sick. I mean, let's hope they're sick, right? Man, you guys, my S rate's looking more and more like a 50, not like a 75. And we're all about some S rates. So you know about the S rate? The success rate. We're supposed to have a success rate of 75%. I think if you're here, I have to pass you. I mean, it's almost a university rule at this point. I mean,
You say that a lot, but I never know if you're serious.
ah. Oh, no, leave it on. You're fine. You didn't turn it off, did you? Okay. Oh, yeah. Am I serious? I am serious. If you finish the course and complete all the homework, there's a pretty decent chance that you will pass, yes. But you do actually need to show me that you have at least a complete mastery of the basics in here if you want to pass. I mean, if you can't integrate by parts basic stuff on the final, I won't pass you. It's true.
Will that be on the final?
Will basic integration by parts problems be on the final? Yeah, definitely. In 2 hours, you got, for 2 hours, I mean, that's 30 problems, right? I mean,
I can't get to 8 problems in 2 hours.
no, I try to pick. All right, these are my notes. So these notes actually have some pictures.
Is this for your notes online?
What's that?
Is this from your website?
Yeah. This is. It's probably the ones I have posted. This is page 350-ish. What's that? Make what myself? Yeah. Oh yeah. Oh yeah. It's well, I had a class in HTML in college. I actually had my introduction to the university course. We had to make our own web page. Yeah, like at NC State, each student has their own dedicated web space. In the late 90s, yeah. I know, right?